So this presentation is about finding the p-value of a sample mean when you do not know the population standard deviation sigma. This is very similar to the previous presentation where we did know sigma. In fact, we're going to work through the same stories again, just taking out the part of the story that tells us sigma. Now, you need to go through the previous presentation with known sigma first. It's a little easier to understand, and this one will be a bit brief, standing alone, so I think it's better to do the one with known sigma first. So here's an example of a right-tailed p-value problem with unknown sigma. As before, we come into this with the Blue Cross Insurance Company has an existing belief, a null hypothesis, that the mean temperature of their customers is 98.1 degrees Fahrenheit. It seems a little low to us. They do not this time offer any hypothesis about the standard deviation. Well, our fictitious character Anne sees that 98.1 and she says she thinks that's a little low. She offers the alternative hypothesis that the population mean is greater than 98.1. And she goes out and she collects some data to try to support her position. She gets a simple random sample of 36 customers, and she finds that their sample mean is 98.6 degrees Fahrenheit. And she also calculates the sample standard deviation for just these 36 customers and gets 0.69 degrees Fahrenheit. So she thinks she has evidence against the null hypothesis. And her task, if she wants to convince Blue Cross that they are mistaken, her task is to calculate how strong is her evidence. She'll do this in the form of a p-value. So this time, as always, we want to start by drawing the distribution curve, and we cannot use the central limit theorem because we don't know the population standard deviation. Okay, we use that formula, statement 2 from the central limit theorem about you take sigma, divide by the square root of n to get the standard deviation of the sample mean, but we cannot do that because we do not know sigma. Well, fortunately, we have Gossett's theorem instead of the central limit theorem. To use that, we still need to have a simple random sample. The story tells us that we do. And we still need to have either x is normal or the sample size is at least in the low 30s, and it is. We have a sample of size 36. So those two things together, simple random sample and a big enough sample, and x is normal besides, that tells us we can use Gossett's theorem, and it tells us that the t-statistic has a shape. It looks a lot like the normal distribution, but it's a different formula that Gossett worked out, not the one that Gauss worked out for the central limit theorem. That normal distribution curve was a formula that Gauss figured out, but this is a different, slightly different formula, slightly different shape. The t statistic, what it is it's you just take your sample mean and convert it into approximate standardized units. It's almost just like standardizing, but if you were converting to STDs really, you would need the sigma down here. You would need sigma to find z, but we're using the sample standard deviation instead of sigma. And so we come up with a new letter. Gossett used the letter T. So that's just the approximately standardized value of the sample mean. And because of the S on the bottom that changes every time you get a new sample, it changes the distribution of T. So you do that, and you get your T-score is 4.35 STDs. And now the question is, what's the probability that Anne could get such a big T-score just by accident if the null hypothesis was true? So she needs the area to the right of 4.35 STDs. The built-in Excel function, tdist, only tells you the area to the left. And that's why you need this 1 minus in order to get the area to the right instead of the left. And so Anne does that calculation, and she gets 0.06%. And that's bigger than she had last time when we knew sigma, because the t statistic is more spread out, more variable than the z statistic, more uncertainty about it. But it's okay, it's still pretty small. So Blue Cross is going to push her the way they did before. They wonder if they might be right about the sample mean, the population mean being 98.1. But Anne says, if it was 98.1, then only this tiny percentage of all possible samples would be so big like mine was. So either I got one of those unusual samples, or else the null hypothesis was just wrong. And because the p-value is smaller than the significance level, p-value is less than alpha, that's when you reject the null hypothesis. So Blue Cross is convinced that this evidence is significant. And Anne gets a raise. Okay. Now here's, as in the previous PowerPoint, the example with the city of Bozeman arguing with Montana about whether the population mean water usage is or is not 125 gallons. This time, we're not given the population standard deviation. Okay, now this is subtle, because, you got to watch out for this. See, look at the wording here. People look at this and they say, I do have the standard deviation. 10 gallons, just like it was in the previous story. But no, you've got to pay real careful attention to the words. You see, this time it's the simple random sample that had a standard deviation of 10 gallons. In the other PowerPoint, it was the population that had a standard deviation of 10 gallons. That makes all the difference. So you have to pay attention when they tell you the standard deviation. Look at the subject of the sentence here. Notice, was it the sample or was it the population? So because we do not know the population standard deviation, now we're going to have to do a t-test, not a z-test, at the 5% significance level. So, what lets us draw the t-curve? One, we have a simple random sample, and two, even though the sample size 10 is small now, X was given to be normal. It's part of the null hypothesis. So that gets us in the door, and we can use the t-distribution. It's two-tailed because the alternative hypothesis just has this not equal to symbol. And so we approximately standardize our sample mean using the 10 here for the sample standard deviation. We double it. Well, we calculate that we shade both ends of the distribution. And then the p-value is the area of those two tails together, twice the area of one of them. You get a little bit more than before. Last time it was like 13%, now it's 17%. The evidence now against the null hypothesis is even weaker than it was before. That p-value is not less than 5%. So Montana is not convinced that they're wrong. They see you have some evidence against their hypothesis, but they're not sufficiently confident. You've not met the burden of proof that's on you. So they're going to send you out to get more evidence. If you get a bigger sample, you'll be able to, you'll either get stronger evidence against the null hypothesis, or else you'll, if you still fail to reject the null hypothesis, even with a really huge sample, you're going to give up after a while, And so maybe there are only two kinds of hypothesis in the world: the ones that have already been rejected, and the ones where at this point everybody's given up, because they've been unable to get strong evidence against it. So if it's not right, at least it's close enough that you can use it. Yeah. So we had weak evidence against the null hypothesis. That's it.